Okay, so for our final week, we have this mini chapter on examples of functions. We had to postpone it to here because we needed enough algebra really to talk about these. Now, these particular examples of functions we're looking at are typically going to be real numbers or possibly just positive real numbers to real numbers or possibly just positive real numbers. So we're going to have a number of examples. So one is lines. Now, to talk about lines, we need to talk about the concept of slope. So a slope is can be attributed is a number that describes the steepness of a line or a line segment. Okay. So how does it work? Well, say you take 2 points on the line segment and you look at the ratio of how much you go up as you go across. Okay, so say if I call this how much you go up and that much you go across, the slope of this line is how much you go up, which can be positive or negative, divided by how much you go across. And you get this, there's a slope formula that we don't actually have to talk about here, so I don't have to introduce it. So this is what slope is. A vertical line, which would be infinite slope because you're going up, it would be division by zero. In fact, it wouldn't be defined, isn't a function by the vertical line test. So we don't have to consider infinite slope. So what we have here is let m and c be constants. So there's some specific real numbers, like whatever, 2 and 3.4, whatever. The graph of a function from real numbers to real numbers given by L of x is equal to some constant times x. Sorry, this constant times x plus this constant. If you graph this function, you get a line. Okay, so I think we are going to come up with a proof here. So suppose that you have any 2 points that satisfy the equation of the curve. So the idea being, so input, output, input, output. So I think what we're saying here is, let's say do the first one. So y1, which should be L of x1, would be equal to m of x1 plus c1. So the input x1, you get out mx1 plus c. There's no c1. And then the other one is y2 is equal to m times x2 plus c. And take away one from the other. I think we'll do this one minus this one. So here what we're doing is we're going to do, if we were to write this down as a function, by the way, so this is something actually you've been doing with simultaneous equations. So what we're going to do is we're going to the first function, or sorry, to the second equation, we're going to take away y1, and we're going to apply a different function to, well, what looks like a different function to the right hand side. We're going to do take away this. But because these things are equal, y1 is equal to this, taking away y1 is the same as taking away mx1 plus c. Same thing. So we end up with y2 minus y1 is equal to mx2 plus c, take away mx1 plus c1 plus c, excuse me. And what you end up with here is, let's go on the next page. So what I'll do here, and there's not much space for this, so I get c minus c, that's gone. I'll take out the common factor of m on the right hand side. I get y2 minus y1 is equal to m times x2 minus x1. And what we're going to have there is, I'm going to divide both sides by x2 minus x1. Now these are supposed to be two different points, and that means that x1 and x2 are different, and so I can divide by x2 minus x1. If they were the same, I'd be dividing by 0, which is undefined. And writing it the other way around, you end up with m is equal to y2 minus y1 over x2 minus x1 is constant, because m is constant. And what is this? Well, if you go back to our picture and write in some coordinates, so this would be x1, y1, and this would be x2, y2. And so this slope, well, what's this distance? Well, this is y2, This is y1, so this distance is y2 minus y1. And then this is, if you look at it, so this is x2, so that's the distance from here to here. Take off distance from here to here, you get that distance there, which is something that should be familiar to you. So what you see is if you take this function, plot it, and you take any 2 points on the graph, you can show that the slope between the 2 points is the same. And that's what a line is. So that's a proof that this is in fact a line. So that is any 2 points on the graph have the same slope between them, therefore the graph of L is a line. Let x equal 0 and you get L of 0 is equal to m times 0 plus c. And of course m times 0 is just 0, 0 plus c is just c. So this is 0 in, c out. So if I draw this here, I might draw another one as well because there's something I want to show. And a third thing I want to show. Okay. So this we'll call L1 of x is equal to mx plus c. And the point is at x equal to 0, y is equal to c. So 0c is a point on the graph. In other words, mx plus c cuts the y-axis at c. Now this is a positive slope, so it goes up. It goes up, so it's a positive slope. Now this one has 0 slope because it's flat. So this one would just be L2 of x equal to 0x plus c. 0x is 0, so this is just constant function. And then this one here would be, say L3 of x is equal to mx plus c, but because it's going down, the slope is negative. So for example, minus 2x, for example. And this allows us to easily sketch lines. Okay, so basically we've got the same picture here again. And the question is, it's basically this same picture. And the question is, which of these are invertible? So when is a line invertible? If you look at the red one, now by the vertical line test doesn't say anything, but the horizontal line test for this, every horizontal line will cut that once and only once. That it cuts it at least once means it's onto, and that it cuts it only once means it's 1 to 1. So it's onto and 1 to 1. So if m is bigger than 0, it's invertible. Similarly, if m is negative, it's invertible. But this one isn't onto. It doesn't hit, for example, y equals 0, and it hits c multiple times. So L of x equal to m of x plus c, where m and c are constant, is invertible, as we just explained, if and only if the slope is non-zero. Okay, so lines are these things where the m is non-zero and these are constants. Right, a quadratic function is a function of the form q of x equal to ax squared plus bx plus c for constants a, b, and c. So if you're, and they're real to real. Now what are we going to look at? It can be shown, and this is all we're going to care about, is that the graph of a quadratic with an x squared looks like the graph of x squared. Now the graph of x squared is a u. So this is supposed to be the graph of x squared. If your a, the multiple of x squared, is positive, it's going to look like this. It's going to be happy. So that's a bigger than 0. And if the leading term is negative, it looks like it's a sad shape. I think that's all we need to know at this point. Now you can push this a bit further. What about if you don't have just x squared? What about if you have x cubed or x4 or up to x to the 10, whatever you want? So these are called polynomials. So I'll write down some examples of polynomials. So P1 of x, a line is a polynomial. Say 2x minus 3 is a degree 1, the degree is the highest power. Let's do a second polynomial, say x squared plus x, sums of powers of x, highest power is 2. Let's draw another, say p of x is equal to say x to the power of 10 minus 2. This is degree 10, and let's take another one, say x to the power of 55 minus x to the power of 11 plus 2x squared plus 11. This is degree 55. Okay, lines are degree 1 and quadratics are degree 2. In general, a polynomial of degree n has n roots. Okay, so there's one thing we should note here with the x squared in general is, so think about the coordinates. So this is say x1, 0, and this is say x2, 0. And because of the shape, they're going to hit, in general, hit the x-axis at most twice. They can hit them once, like x squared, or not at all, like x squared plus 1. And look at these, number in, number out. These are called roots. So a root, in the context, particularly of a real function, is a number that you put in and you get out 0. And in general, a line has only one root, a quadratic has 2 roots, a cubic has 3 roots. This in general has 10 roots, well it's at most 10 roots, and this would have at most 55 roots. Some of them can be repeated, which is something I don't have to get into, and some of them can be unreal, which we don't have to get into either. Now the growth rate, so this is, the growth rate is really what happens for big X is dominated by the highest power. So for example, if we look at these functions here, p1 of x is approximately 2x, and we'll explain this in a moment. p2 of x is approximately x squared, just take the highest power. p3 of x, I'm just gonna put a 7 in front of this for argument's sake, and I'm going to change this to a minus. Okay, so p3 of x, so this symbol is basically saying what's the growth rate, and as I said, I will explain this in a moment. And p4 of x, approximately 7 times x to the power of 55. So the idea here is that when you have a big number x, now there will be a further remark in the notes which you can read if you want to understand why we're interested in this. It's connected with algorithms. So basically the idea is that if x gets, so x is a real number, it's some input. If you start putting in very, very big numbers, like if you're looking at 2x minus 3, really for a big value of x, let's say if I put in, say just x equal to 2,000 for argument's sake, there's essentially 2x minus 3 is very, very close to 2x in the sense that the percentage difference between them gets very, very small. So like the difference already at x equal to 1,000, the difference between 2x minus 3 and 2x is very small. It's less than, well less than 1%. And as the value of x gets bigger and bigger and bigger, this will happen more and more and more. So for example, the difference between these is always 3. And like say if you put in 10,000, or just any big number really. So this is the ratio of the difference between them to the true value. It gets tiny. So essentially when x gets big, these look very, very similar. On a graph, they basically look the same. Now here, as x gets big, x gets big itself, but x squared gets big even faster. Like if you're comparing 10,000 versus 10,000 squared, there's a big difference between them. And as x gets bigger and bigger, the x squared dominates. Like a billion squared plus a billion is really just a billion squared plus a relatively small bit. And a similar story here, the minus x to the 10 dominates, and here the 7x to the 55 dominates. So these are the leading terms. So if you're trying to say the growth rates, and this is how I write it, this is the biggest one because it's x to the 55, then this, then this, then this. The highest power determines how fast they grow. So we'll be seeing this a bit later. We're writing like P4 much, much bigger than P3, much, much bigger than P2, much, much bigger than P1. And this is to be understood in the context that if you actually graph them and x getting big, this will be way, way bigger. So like if you take, we'll draw just a picture of some of these. So like if you compare these two, while 2x goes like that, and is initially bigger than x squared. As you get big enough, x squared gets way bigger. And so this is a manifestation of the fact that p2, x squared, eventually gets way, way bigger than p1. You can go push this a bit further if you go into analysis of algorithms. And here you'd say really it's just a multiple of x. So you write that this is in order x. Now I won't explain what this is, but the idea is that the important thing is that it's x to the power of 1. The important thing here is that it's x to the power of 2. The important thing here is that it's x to the power of 10. The minus doesn't even matter. Here the important thing is that it's x to the 55. But all I want you to understand is that the highest power dominates when you're looking at the growth rates, and the higher the power, the faster it grows. Okay, so like you could plot these two, and eventually this one will be way bigger. Okay, exponentials. So you can define e to the x. Now it goes from real numbers to positive real numbers as the unique function such that the slope at each point is equal to the y value, and e to the 0 is 1. Now you can do that, or well, we won't get into that too much. So the graph looks something like this. We should have seen it before, and the growth gets really, really big. So that's exponential growth. So the graph of the exponential function e to the x, e is an actual number. Note that e to the minus n, so this is in the region e to the minus n, it goes to 0. Because negative powers mean division, and e to the n gets really, really big, goes to infinity, so 1 over a very, very big number is a very, very small number. So that's why it goes that way. It's 1 to 1, because every horizontal line cuts it once and only once. It's onto the positive real numbers, and it's bijective, and its inverse is log. Okay. We might also be interested in e to not x but a multiple of x. So for example, e to the 2x. Now these functions look pretty much the same, but the bigger the number here, the faster they grow. Okay, so if I was to draw these functions here, it might look something like this. This can be e to the a2x. Now I really should exaggerate that. It's really growing much faster. And then the other one, now they're both equal to 1 at 0. And then this would be a to the a1x. So this one, if a1 is bigger, so for example, e to the 3x will soon get far, far bigger than, say, e to the 2x. So I'm going to say, for example, look at the difference between e to the 3 by 100. That's possibly too big a number to even look at. That's e to the 3 by 10 minus e to the 2 by 10. The difference between that is enormous. So it's the multiple of x here that determines how fast it grows, and the bigger the multiple of x, the faster it grows. Okay. Exponentials eventually dominate, are much larger than any polynomial. So like you might have a polynomial that, say, it can do whatever it wants initially, so it does some weird stuff. Eventually the leading term dominates. Okay, and you can have, so this is some polynomial, sums of powers of x, and then an exponential might, now initially it might be slower growing, but eventually it gets way bigger. This would be an exponential function. So this is why, this is, you compare exponential growth with polynomial growth. And polynomial growth is fast, but exponential growth is far bigger. So for example, look at this e to the 0.001x. Like if we put in, let's look at it at x equal to 0 versus, I have to be careful here now what I put in. I'm not sure what I can actually put in here, because the calculator, I think, like the numbers are getting too big for the calculator to even handle. I think if I take logs here, I might be able to do it. It's impossible to even say. So basically, so for, say at x equal to, I can't even think of a number I can put in. Can I put in 2, even 0.5? So I think at x equal to 0.5, this number is, well, it's kind of messy. It's hard to say it right. So basically what happens is for quite a while, this number is actually not that big. Like for example, e to the power of 0.001 by 10, it's very small, whereas 10 to the power of 10,000 is enormous. But if you keep putting bigger numbers into this, it gets bigger and bigger and bigger. And eventually it gets so big that the calculator can't handle it. So even though this is initially very, very small, eventually it gets way, way bigger. So eventually what you'd say here is that e to the 0.001x, and in fact any positive exponential, is much, much bigger than any polynomial, which is just sums the powers of x. Now, if you have negative exponentials, they look like exponential functions backwards though, because instead of putting in positive things, you're putting in negative things. Instead of putting in negative things, it's positive things. So the graph will look like the mirror symmetry. So if you have a negative exponential, what it actually does is, so this is drawing an exponential backwards, as it were. It goes to 0. So this is, say, y equal to e to the minus bx. As x gets big, e to the minus bx gets small, it goes to 0. And the larger the value of b, the faster it goes to 0. This also can be seen on the previous page, although we didn't quite make it out. If an exponential grows faster over here, it'll go to 0 faster over here. Okay. I think we're going to do a little question here. So, let's see. So the graph in the diagram matches which of the functions. So the idea, what you can always remember, is that in the graph, it's all the points of the form input, output. So we can kind of test it like that. So here the obvious thing is, look at the point here, x equal to 0, y equal to 10. So whatever it is, if you put in 0, you must get out 10. If you put in 0 into this, what happens? 5e to the power of minus 5 times 0. Now, minus 0.5, times 0 is 0. E to the 0 is 1, so 5 by 1 is 5. So that one doesn't work. Put in 0 into this, you end up with e to the minus 0.5 times 0. Now, minus 0 is just 0, so that's e to the 0. E to the 0 is 1, so you end up with 0. And the only one that actually works is c. So this is the right one. Okay, but you can see it anyway. You don't actually technically... You can rule, well, maybe we should look at all of them, but yeah, probably should look at all of them. So here's this graph, find the values of a and b. So the first thing we should do is, this is what's happening at x equal to, or even t here rather, t equal to 0. So you get in t equal to 0, look at the coordinates, t equal to 0, y equal to a. So we put in t equal to 0 into this, we get out a. So f of 0 is equal to 5 plus 3e to the minus 2 times 0. And minus 2 times 0 is 0, e to the 0 is 1, 3 times 1 is 3, 5 plus 3 is 8. So we know that a is equal to 8. And then we know that if we look at 5 plus 3e to the minus 2t, we know that negative exponentials, as t gets big, so this represents t big here, what happens to negative exponentials? They go small. So this bit goes to 0, and so this whole thing goes to 5. So we know that b is equal to 5. So that's how that question will go. Okay, so we'll look at logs now, graphs of logs. Just remember that logs are inverses of exponentials.